Have you ever wondered how heat moves from one place to another? In this video, I will explain the three modes of heat transfer: conduction, convection, and radiation. We will also see simple examples and how these processes are used in industry. Let's get started.
First, let's talk about conduction. Conduction happens when heat travels through direct contact. For example, when you place a metal spoon in hot water, the heat travels from the hot water to the spoon. This happens because molecules in the spoon collide with each other, passing energy along the materials. See how the spoon gets hot. That's how conduction action happens.
Okay, next, let me explain to you conduction equation. Let's take a closer look at the conduction equation below. Q equal to negative K A D T over dx. This equation helps us calculate the rate of heat transfer Q through a material by conduction. Let me explain one by one for you. Q is the rate of heat transfer measured in watts. It tells us how much heat flowing through the material per second. K is the thermal conductivity of the material measured in watts per meter per Kelvin. It represents how well the material conduct heat. For example, metals like copper have high thermal conductivity, while materials like wood have low thermal conductivity. And A is the cross-sectional area of the material in square meters. The larger the area, the more heat can flow through. And lastly, dT over dS is a temperature gradient which shows how the temperature change over a certain distance. The higher the temperature difference or the thinner the materials, the faster the heat will flow. And lastly, the negative sign in the equation indicates that heats flow from a region of high temperature to low temperature opposite to the direction of the temperature gradient. To summarize, the conduction equation helps us understand how heat moves through material and how factors like thermal conductivity, area, and temperature gradient influence heat transfer. This is principle behind everyday things like cooking utensils, building installation, and heat exchanger.
Next, we have convection. Convection occurs when heat is transferred through fluid or gases by the movement of a heater. For example, when water boils, the hot water
We need to
rises
know
while the
each
cooler water
situation
steams,
like
creating a
conduction,
cycle
convection, and
called
radiation
convection
have
current.
each equation, or we call it as step by step to solve the
Right here we can see the
problem.
bubble rise
Okay, so
because
this
of
is the
convection
equation that we need to use.
current.
Last step to find the rate of heat transfer. But in this, we cannot directly use this equation for first step because we doesn't have the question did not give the hash value. So convection divided by two types. It's natural and forced convection. So firstly, I would like to explain about solving a natural convection problem step by step. First, we need to calculate the temperature film Tf by using the formula of Tw plus Tb. Tw is for surface or wall temperature, Tb for fluid or bulk temperature, and we need to divide it by 2. Next, we need to find some properties from the table at Tf that we got from first step. This include density, thermal conductivity, dynamic viscosity, and Prandtl number. If the temperature is not listed in the table, we you need to do interpolation by using the formula y equal to y1 plus x tolak x1, y2 tolak y1 divide by x2 tolak x1. After that, you need to calculate thermal expansion coefficient, or we call it beta, 1 divided by TF. Okay, next step number 4, you need to calculate greatest of number, that's the S. GR equal to GP delta T L 3 divided by dynamic viscosity squared. So after that, step number 5, you need to calculate the Rayleigh number. Rayleigh number state as RA equal to GR darab PR. Next, you need to calculate the Nusselt number. The Nusselt number depend on situation. The situation is vertical plate or vertical cylinder, horizontal plate or horizontal cylinder, and supply. So you can see the equation that I have right in the picture, the equation for each situation. Okay, lastly, you need to calculate the heat transfer coefficient. From the equation, you need to solve h. So you need to move the h to the other side. That we will get the equation h equal to nu darab k divided by f. Secondly, the force convection step by step. It seems similar to natural convection, but we have a step that not similar to natural convection. Let's go through. Okay, firstly, we need to find temperature film. Secondly, we need to look up properties at TF in the table. Density, thermal conductivity, kinematic viscosity, and part number. If the value is not directly in the table, as usual, we need to do interpolation also. Now, we need to calculate Rayleigh number 3. Where is V is the velocity, LC is the characteristic length, and V is the kinematic viscosity. After we calculate Rayleigh number, we need to calculate Nusselt number depending on the situation that given. For flat flats, we need to check the flow is laminar or turbulent. For laminar, we need to use the equation NU 0.664 RE 0.5 PR 1/3. For turbulent, we need to do NU equal to 0.0366 RE 0.8 PR 1/3. For cylinder, we use the estate in the pictures. For supply, we need to use the estate in the pictures also. Where for supply, where US is the viscosity of the surface, that we need to do the calculation equation. Okay, after that, we need to calculate the heat transfer. Heat transfer is the last step that we get. Oh, before I forget it, we also need to using the same equation as natural convection to find H, such like H equal to NU darab K or divide by L. So after that, we will use the formula for heat transfer. So that's all from natural and force convection equation.
Okay, finally we have radiation.
Radiation is a heat transfer through electromagnetic wave. Unlike convection and conduction, radiation doesn't need medium to transfer heat.
Imagine you are lying on a beach and feeling the warm sun heat up your skin. But how does the heat from the sun reach your skin? Is it by conduction or convection? It can't be. Conduction and convection both require particles for heat transfer. But there are not enough particles in outer space between the sun and Earth to transfer heat in this way. So then, how does the heat get transferred to Earth? The answer is via radiation. Radiation allows for the heat from the sun to reach Earth via solar radiation, which is a collection of electromagnetic waves. Electromagnetic waves can travel through a vacuum, such as outer space, as they don't need particles to travel. This collection of electromagnetic waves include gamma rays, infrared, UV light, and visible light. Solar radiation is comprised of approximately 40% infrared wavelengths, 50% visible light wavelengths, and 10% ultraviolet wavelengths or shorter, which includes X-ray and gamma waves. Heat from the sun isn't the only way you would have felt heat radiation. If you stand in front of a fireplace or radiator, you will have felt heat radiate from it. Yes, a fireplace or heater also causes heat transfer via convection in a room, but it also radiates heat via electromagnetic
This
waves.
equation is used to calculate radiation heat transfer between a surface and its surroundings. It takes into account the energy radiated by the surface and the energy absorbed from its surroundings. Q represents the net heat energy radiated per second by the surface. This value can be positive or negative. Next, Stefan-Boltzmann constant, a universal constant, equals to 5.676 multiplied by 10 power of negative 8. It relates the thermal radiation of a black body to its temperature. It also ensures the units in the equation are consistent. A. Surface area, the total area of the radiating surface. Larger surfaces radiate more heat. And lastly, T, surface temperature, absolute temperature of the surface in Kelvin. The fourth power indicates that radiation increases exponentially with temperature. For instance, if T doubles, the radiation increases by 2 to the power of 4, goes to 16. Multiply. We also have emissivity in this equation that is dimensionless. It measures how effectively a surface emits radiation compared to a perfect black body. It has two types of range. First, emissivity equals to 1, perfect black body. Second, 0 less than emissivity less than 1, real surface, that is for gray body, and it radiates less efficiently. The radiation equation has numerous practical applications in engineering, science, and daily life. It is widely used in designing and analyzing heating and cooling systems, such as radiators and heat exchangers, to optimize energy transfer. In building design, it helps estimate heat loss through walls, windows, and roofs, allowing engineers to develop effective insulation systems. The equation is also essential in understanding and predicting the thermal behavior of objects in extreme environments, such as spacecraft exposed to solar radiation or heat shields during atmospheric re-entry. In astrophysics, it is used to calculate the energy radiated by celestial bodies like stars or planets. Additionally, industries use it to monitor heat transfer in manufacturing processes such as drying, welding, or material processing. Overall, the radiation equation is a fundamental tool for managing and understanding thermal energy exchange in various practical scenarios.
Conduction is used in designing cookware like pots and pans and in heat exchanger to transfer heat efficiently. Number 2, convection. Convection plays a major role in heating, ventilation and air conditioning system, HVAC system, to circulate air and regulate temperature. 3. Radiation. Radiation is used in solar panels to convert sunlight into energy and in infrared thermography for detecting heat pattern.
To sum up, conduction, convection, and radiation are the three-way heat transfer. Each play a unique role in our daily life and in the industry. Understanding these processes help us innovate and solve real-world problems. If you find this video helpful, please like, share, and subscribe to my channel for more educational content. Thanks for watching. Bye.